good afternoon everyone. We welcome you to the second session of 1 week online ISC approved faculty development program on recent trends in RF and microelectronics, organized by Department of Electronics and Telecommunication Engineering, Don Bosco College of Engineering, and Department of Electronics and Communication Engineering, National Institute of Technology, Goa. Technically sponsored by IEEE Bombay Section, WIE Affinity Group. For this session, we have with us an eminent personality, Dr. B. Satyanarayana. He did his BTech in Electronics and Communication Engineering from JNT University, Hyderabad, and PhD in Physics from IIT Bombay. He is working in the Department of High Energy Physics, TIFR, since 1983 and is currently a scientific officer H. He is also visiting professor at the Applied Science Department of the American College, Modular. His areas of interest include detectors and instrumentation for high energy and nuclear physics experiments. Dr. Satyanarayana has published about 250 research papers and proceedings in national and international journals and conferences, besides scores of invited talks. His very first paper won the Best Paper Award by Institution of Electronics and Telecommunication Engineers. Dr. Satyanarayana is a fellow of Institution of Electronics and Telecommunication Engineers as well as Institute of Engineers. He is a member of the Governing Council of Instrument Society of India as well as a member of Indian Physics Association. He guided a large number of doctoral, master and undergraduate students. He served on many of doctoral and expert committees as well as academic councils, board of studies and advisory boards on colleges and universities. He is on the editorial and referring teams of several prestigious science and engineering journals. Dr. Satyanarayana is a senior member of IEEE. He is currently an executive committee member and vice chair of IEEE Bombay Section, as well as the chair of its Signal Processing Society. He previously served as the secretary of the section as well as chair of its technical and professional activities. He also served an executive committee member as well as vice chair of the IEEE India Council. He won IEEE Bombay Section's Outstanding Volunteer Award for 2014 and IEEE Headquarters MGA Achievement Award for 2016. I request you, sir, to take over the session.
Sir, can you hear us?
Yes, I can.
Yes, sir. We request you to kindly take over the session now. Sir?
Yeah?
Yeah, you can start the session, sir.
Okay. Okay.
So shall I share my screen?
Yes, sir.
Okay. Is my screen visible?
Yes, sir, it is visible.
Okay. Okay. So shall I start?
Yes, sir.
Okay.
Okay. So good afternoon, everyone. I hope you had a nice inaugural session of this FTP program and also had the first session. So I understand that this is the second session in the FTP program. Of course, I was asked to kind of talk generally on the microelectronics um, for the RF signal processing. Of course, I made slight changes in the title to kind of say more on the advances that are happening in the microelectronics and which are finding newer applications in the RF signal processing. So just a kind of ornamental change in the title. Otherwise, it remains the same. I also realized that that there are three more lectures in the FTP program talking generally on the microelectronics or related to electronics in general. Uh, but I see that many of the theoretical, domain topics are still to be covered. They will be covered in the following days. So I hope when you kind of finish the entire FTP on, let us say, Friday, then it actually makes a sense on what I'm kind of talking. Just in case you don't know me, I work in the Tata Institute of Fundamental Research, and my interest, of course, is apart from other physics interests, to kind of design electronics, design, let us say, VLSI, microelectronic circuits, which our main purpose, of course, is not is different from on what I'm talking today, but it is more on signal processing of the signals which are coming from so-called sensors or detectors that we use in the science experiment. But I do see, of course, a lot of synergies between what I work on and what I do, and what is relevant to today's topic, namely the radio frequency signal processing. So I hope I will share with you certain excitements that are happening, particularly in the microelectronics field, which of course has far-reaching applications in the RF signal processing. Okay, I understand the program itself is an IEEE sponsored, technically sponsored, I would say, event, and it is only befitting that I kind of flash the very first slide uh, on the. Of course, you all know about this. This is a very elementary information. On the frequency spectra that we generally talk about. Where does IEEE come in the picture? It's just because, just like many things that you'll also hear later in my talk, IEEE works on lots of standards which are particularly of interest to us today. And then even this definition of the spectra used in various fields and industry and areas also is actually named after the standard that is put by IEEE. Of course, we start here from very low frequencies, maybe few tens of hertz, go all the way to about 3,000 gigahertz. They kind of encompass, as I said, large number of fields and the applications. Okay, but one general that we all know, which we of course teach to our kids, the students, is that as the frequency increases, the wavelength decreases and reduces to kind of dimensions. Well, that is what most important. which is comparable to the size of the circuit boards or even sometimes to individual discrete components which we use. So starting from, I mean, if you are at an extremely low frequency or even for that matter, voice frequency, which is like, hundreds of kilometers, you actually get down by the time you come to, let us say very high energy frequency or ultra high energy frequency, you come into few tens of centimeters. Obviously, when you use a cell phone, the cell phone is few tens of centimeters just because it handles the frequencies which are of the order of about a couple of gigahertz, right? That is an important aspect that we must address because, for example, okay, it is actually governed by the lambda wavelength is C by F. F is the frequency that we are talking. So therefore, if you really look at some of these numbers and the wavelength here, you will find that very, of the order of about 30 gigahertz, 30 megahertz, you will see, let us say roughly 10 meters, then at 300 megahertz, it goes to about a meter. But when you go to 30 gigahertz, you're actually talking about the lambda, which is almost to the size of the circuit components, which is 1 centimeter. Now, as I mentioned, when you actually come down to the VHF area, so that is where the wavelength starts reaching dimensions which are equivalent to the physical extent of the electronic system. Because when we build an electronic system, doesn't matter whether it is an amplifier, whether it is some mixture, or whether it is some power supplies, preamplifiers, power amplifiers, low noise amplifiers, whatever. I mean, the entire system is typically of the dimensions to where the UHF frequencies reach to at this point. Okay, so at this, when you come to this region, so you have to take into account, the electromagnetic wave nature of the current and voltage, right, of the signals. Okay, so of course, when you have at zero frequency, there's no issue, no matter. I mean, you never even think of considering those frequencies because they are equal to zero, and then the wavelength is infinite, it's always present there. But when you actually come down to this level, you have to really see that actually your signal is actually following, or signal can be current or voltage, it's following the wave nature. Now, now, if you want to kind of give a little bit like I mean, it's not a hard kind of a definition, but if you customarily, that's what I say, customarily, the RF frequency is basically starting somewhere from VHF region and all the way up to the S band, which is, let us say, about 4 gigahertz. Okay. Now, after that, you also have the microwave, which again is a kind of a norm or a traditional associated with mostly systems like the radar or the warfare systems and so on, operating mostly starting from C band and above, which is, so you have RF, which is roughly here, and then then microwave, which is just following right after. So these are some kind of, I think, rules of the game, if I can call that. Once again, very elementary kind of a introduction just now. When you talk about any RF technology, typically you talk about something like where you actually transmit certain signal and something where you actually receive the signals, and to a certain extent there has to be a synergy between them in terms of the clock frequency. Now, if this is the so-called low frequency chipset, which means actually where I produce or process the data, and this is obviously at a very low frequency, and then voltage control oscillator, then I kind of drive them with a power amplifier and drive into a kind of antenna, right? Now, the same signal, if I were to receive it, then of course, just like a filter that I have on the output, I'll have a filter input. The low noise amplifier, once again, I might want to put another filter after the amplifier, then use the same VCO to kind of mix it and get the actual signal extracting out the carrier oscillating frequency. Then once again, I get down to kind of acquire the signal that was kind of modulated on top of carrier. So this is, of course, doesn't matter. It's a very generic kind of a system. It can be applied to varieties of varieties of systems that we will keep talking later. Uh, as I already mentioned in the previous slide, the radio waves, of course, is a form of electromagnetic radiation. And we also defined roughly this kind of a frequencies from very low frequency to almost about 300 gigahertz. The RF propagation, typically because these are electromagnetic waves, thanks to Maxwell, they travel at speed of light. So you might say that it actually doesn't require any medium like air to travel. And as I said, since I come from the basic science research background, in our labs, in our experiments, in our research areas, we work with the radio frequency waves, or in other words, the electromagnetic radiation, which is actually occurs naturally, in the universe. For example, we study what we call sun flares, which is an effect of the big flare that is coming up once in a while in the sun. Sometimes we study lightning. We study lots of electromagnetic radiation coming from sun and the stars and so on in the space that radiate RF waves as they kind of age. But that is naturally happening, of course, in the human when we develop our systems and we actually communicate because we artificially create electromagnetic radiation with this kind of circuitry and at oscillated whatever frequency that we choose. And many times, of course, we know RF communication, we design and build for varieties of industries. Sometimes maybe TV broadcasting, sometimes maybe radars, sometimes maybe computer communication, mobile communication, sometimes simple remote control or remote metering, monitoring, and so on. So varieties of applications, but the general philosophy of a system is what is shown on the right. And as I said, just like what is also available, natural sources like stars and celestial bodies produce the electromagnetic radiation, but we actually build these systems by ourselves. Okay, so while many of the individual components that you saw here and here, it could be filters, it could be mixtures, it could be power amplifiers, these can be classified based on what is the operating frequency that you are operating. In other words, when I say I'm designing a preamplifier, then you will be asking me, are you designing preamplifier for this frequency or this frequency or this frequency, and so on. And similarly, the filter, similarly, maybe other components. But you cannot say that I'm designing let us say, a filter for Wi-Fi or Bluetooth and so on and so forth, because these filters or these hardware components only in a communication hierarchy only forms the physical support, right? Physical layer, we call phi support. Now, if today what we are going to talk about, especially the lower frequency chipset and so on, the RF modules, the transceivers, the data send and receive the data, or the so-called system on chips, the entire system of communicating, in other words, processing, acquiring data, etc., is on one chip. That forms the what you call data link, which is on the higher level of the communication 7-layer model, if you consider that. And then when I say this, then necessarily I have to tell that, oh, okay, I'm building a, let us say, a data link for Wi-Fi, data link for Bluetooth, data link for, let us say, for GPS or whatever, various units. So that is the kind of, depending on the wireless communication protocols, then I will be designing that circuit or that system or that microelectronics circuit. Whereas the rest of the components, you will anyway decide and say that this is what I'm going to use for a particular frequency. Whereas on the back end, which we will talk today specifically, I can make a very general purpose design architecture and I can use the same one. It doesn't really matter whether I'm actually sending out on this frequency, carrier frequency, or that frequency, and so on. Okay, so that is the idea. So of course, we all know, and also we agree that the field of RF communication has grown just like any other fields, especially for last 2 or 3 decades, extremely fast. And because these days we use devices which were unheard of at least 30 years ago, 25 years ago, maybe 40 years ago. And the wireless communication is actually something which has become in some way like a because in some way like an electricity. You say wherever you go, there are 2-pin plugs or 3-pin plugs from where you can put in your equipment. And Wi-Fi has become like that, right? And when you reach somebody's home, typically what we first ask is what is the Wi-Fi password. So Wi-Fi has become an ingredient of our life, and it is actually affecting our life in both ways, but it's the most important development. Today we all use cell phones. They're supposed to be a telephone where we speak with our friends and family, but more than that, actually, the cell phone does many other features which have, in fact, killed other industries in some sense. It is an encyclopedia of information. All online shopping that you do, GPS and whatnot, weather monitor and so on. So that is exactly what I meant, how the communication technologies, especially in the field of RF, is driving all other ancillary fields. We can, now we went, if you really look at for a while on the health sector, we are talking about, the patient's brain or heart, or for that matter, all vital parameters of a patient being monitored remotely and then transmit the data on wirelessly, and allowing the patient not necessarily just sitting in the hospital, and they can move around, and the doctor is always looking at the vital parameters and advice and so on and so forth. Of course, as I said, we also use the so-called RFID. That is another great advent that has changed the way we do merchandise, the way we track our pets, cattle, or the wildlife, and the inventory in the godowns. Sometimes maybe our children, and maybe even convicts, maybe the police department must be even if they can install an RFID device. Okay. And just another angle that got attached to the RF technology, which has actually brought in what you today call Internet of Things, has made sure all those devices that we had typically at our homes now become no more you go and switch on them, but actually they all become wireless. Again, thanks to RF for the communication, and IoT, where you typically talk about sensors and actuators and so on and so forth. So this is again a marriage of 2 great technology, maybe 3 great technologies, but obviously as IEEE stands for, advancing technology for the humanity. So that is how the things are moving forward. The main reasons why, let us say, there were advances in the RF systems, as we talked just now. One of them is, of course, because definitely the cost of electronics is coming down as we speak. Probably as I'm talking to you, the cost of electronics is coming down. Okay, I mean, today the best phone, probably cell phone, you will get for maybe 20,000, maybe 15,000. Okay, so but that may be the same as maybe a decade back, 10, 20 years back, but they offer such a kind of functions which are were not possible some time back. So this is the thing. So many frequency bands you are incorporating, many communication modes you are incorporating Wi-Fi, you are incorporating Bluetooth, GPS, everything in your phone, which was, of course, if you remember well, we didn't have all these features in our cell phone some time ago when the cell phones came on the horizon, but they costed similar price. But what one is looking at is today adding up all these communication facilities on top of a processor and top of what exists as a baseband design, right? What I'm actually saying is this affordability, if I can call this as affordable, which means for the same cost you get many more facilities. This actually comes from integration. How do you integrate all these technologies and gadgets together? Okay, So for example, in other words, what I'm saying is earlier, if you remember, many of us designed circuit boards, right? Those circuit boards are very big. They're all made of discrete components. And now we are talking about developing integrated circuits, very large scale integrated circuits, ultra large scale integrated circuits. What are we doing by that? We are actually integrating all that discrete things, everything into a single chip, okay, so that there are hardly any components which are left out of the chip, right? So this is very important. Now, if you see typically any small circuit board, you'll only find that there's one chip that is sitting in the middle, and hardly you will find any other things on the circuit board because whereas earlier, if you look at, there used to be a big board which is actually, kind of spread with lots of components. So this is the integration. Now, of course, when you integrate, you also get some other advantage because this actually happens because I am able to so-called scale the VLSI processes, particularly the CMOS. CMOS is today's technology, and most of the VLSI process is centered around CMOS, complementary metal oxide semiconductor technology. What do you mean by scaling? Scaling we'll see soon, a little later, but how smaller and smaller transistors that you're able to build. If I can build the smaller and smaller transistors, then that means I'll be able to pack within the same 1 centimeter square, let us say, chip, more transistors, which means I can do more integration, which means I can bring everything together on one chip, right? Okay. So, and the second thing is, this is again another thing which is of course not connected directly or closely with VLSI, but there were lots and lots of innovations in terms of directly the RF architectures themselves and various circuits that we deal with radio frequencies, and also various devices that we need to build in order to execute certain RF jobs. Okay, so one side you are talking about the microelectronics revolution, the other side you are talking about RF architecture. So both the domain as well as the platform on which you run the RF domain, both are obviously going ahead hand in hand, and that is what is bringing the main advances in RF systems. Of course, this is quite old slide. I actually picked up from a textbook. So we are talking about here, one is talking about something like up to 2010, so 10 years old story. But if you really look at it, what is actually drawn here is the so-called oscillation frequencies, that means operating frequencies. You can really see that it is, of course, steadily rising. And we are talking about, at that particular time, these were about 200 gigahertz and so on. But you know that we have now much faster systems. And similarly, as I mentioned to you, the scaling, the VLSI processes, the scaling of the integrated circuit node, which we'll again discuss a little bit more. So talking about mid 90s, about 500 nanometers. By the time you reached about 2009 or so, it is 40 nanometers. You will see later, we are now talking about 10 nanometers, maybe even 5 nanometers. People actually talk about 1 nanometer and so on and so forth. So one hand, you're talking about oscillation frequencies. The other hand, you're actually talking about shrinking of sizes. This is what I kind of mentioned on the left side about these advances. As I mentioned in the beginning, of course, the RF systems encompasses many disciplines, and I'm not going to touch any of those disciplines. This is what I said. Hopefully, by the time that you had the FTP program finished on Friday, I hope you'll have a complete picture about what an RF design encompasses. Of course, it encompasses the microwave theory, the communication theory. This is a big, interesting field, which is, of course, I know many of you teach in your first year, second year students, the random signal analysis. This is a very important topic of transmitter and receiver architectures, which we discussed just now. Today, we entirely will focus only on the integrated circuit design and the tools that are these are the tools that are used for designing of ICs, designing of the RF components, and so on and so forth. I'm also not going to talk anything about the wireless standards. As I just now mentioned, IEEE, of course, is the warehouse of about 7 or 8,000 standards, and the so-called IEEE 802 point something itself has dozens and dozens of various standards. The entire wireless standards, there are so huge number. So that is the importance of course, IEEE. And how you multiplex and use the same frequency bands and spectra. This has become a major issue and has a big connotations in terms of what is the cost of access, cost of communication that comes to. And you have seen last 15 to 20 years, it has seen phenomenal kind of effect on how cheap the wireless communication, namely the cell phone, can become thanks to this particular advances in this field. And signal propagation, both wireless, so-called the way we kind of transmit wireless transmission, RF transmission, but also sometimes maybe there are also backhaul network where you also talk about fiber, you talk about very rarely, but sometimes you also talk about copper. So the signal propagation also makes a huge enterprise. So obviously no single person will be able to kind of become an expert, for that matter, not even in one topic, because the advances are happening, as we said, parallelly into many of these fields. So as I said, we'll spend more time today on the IC design or microelectronics. Just one more point, which I think is important to understand here, is that when you say that there are so many interdisciplinary kind of topics to discuss, but they're also challenging, for the RF field to grow. So what are the main issues? What are the main challenges that one kind of RF field actually faces? Just now we said that it actually draws upon multitude of disciplines, which of course requires a very good understanding of all those fields. Sometimes maybe some of these fields you feel that they're irrelevant to integrated circuits. You have to think, because when you focus and we say there's a vertical wall of integrated circuit design, then you kind of try to decouple yourself from the rest of the fields. Now, so the ever increasing demand that for high performance, or let us say low cost, but at the same time a lot of functionality, etc. So how that has made a challenging thing is because early, if you remember what we discussed some time back, the so-called RF integrated circuit design was actually only working like one trans receiver, means one transmitter, one receiver, and plus in that I kind of club some baseband processor. So that is all happens in one chip. One chip means one transmitter, one receiver, and all that back-end side, whatever it is. But today it is not true. Today, people want to make multiple trans receivers, operating not just multiple trans receivers. Trans receivers are operating at different frequency bands, or sometimes maybe different wireless standards. If you remember, we were talking about the link, the data link we are talking about can have Bluetooth, Wi-Fi, GPS, etc. So we are now talking about one chip which has multiple transmitters, multiple receivers, multiple, on different frequencies and different wireless standards. So that is the challenge now. People want to do all that they want to do on one chip. So, of course, earlier, as I said, if I say this is my silicon chip, that was dominated more by the processing one, and allowing the RF circuits or systems, analog designers, some choice where their circuit and devices topologies. But today, since lots of, more than one, multiple basically trans receivers have to occupy a larger area. So therefore, the base band processor space has come down. That's what I told you, because of the integration of larger and larger VLI size systems. Okay. So you remember earlier we used to use lots of these so-called spiral inductors, right? Coils, okay, which used to occupy a lot of space earlier, right? In the older system. But now the design is kind of optimized such that okay, try to use sparingly these coils and so on, because they occupy more space. Okay, so therefore there are challenges. It's not that as if everything is working very nicely. So therefore, there is no challenge. In fact, a bigger challenge than integration is what is shown on the left side, because what are the parameters you talk about? You talk about, I want to have a very low noise. I want to consume very low power. I want to operate at extremely high frequencies at very high gain. I want to probably operate with as low power supplies are possible. And I want to build obviously a system which is extremely linear. Now you can see all these demands sometimes kind of could be like, trade-off. For example, if I tell you, no, I would like to have ultra low noise, front end amplifier. Okay. Now what does it mean? It means that I will need a much higher power. I will probably have to sacrifice a little bit linearity if I want to improve upon the noise. Now, similarly, I can say about if I want to operate at higher frequency, I may require a higher power, I might require higher gain, and so on. So there are some interdependencies. So therefore, I cannot say I want low noise and low power, high frequency, high gain, low supply voltage, extreme linear. No, you can't. So when you actually sit down and design your system, you have to kind of see what are the parameters that I need to trade off, what are the parameters where I can't trade off. So obviously, that is what forms your basic system requirements. Okay, so when I really talk about something I'm sending here with whatever transmitter I have, when I receive it here, I'm actually talking from, let us say if this is my kind of data, which is centered around the baseband. And of course, I kind of do an up conversion and put a power. This is a very generic, simple view, and then send out the data on an antenna. But when I get that back, okay, I know that my baseband shifted to, let us say, frequency, carrier frequency here, and I have to have a very low noise amplifier, down convert back, and then do all my reconstruction of the data using my baseband, right? So no matter what circuit, which we already seen here once, I think this is a repeat in some way, is that you build your actual backend system, and rest of them is kind of comes down to, if I can give an extremely simplified picture, it comes down to using, converting the data into a signal using a DAC, and up convert to push it onto the antenna through a power amplifier. And when I get back again, signals, typically they will be small signals. So I need to kind of take care that I only amplify it very well, but at the same time get a good rejection of the noise, and use the same oscillating frequency so that I can get back my signal. And I use typically analog to digital converter to get back my data, right? So you might say that it actually consists of half a dozen components. So each of these components requires certain important considerations, and the best being here, because this is where microelectronics has helped us to kind of shrink, as we said, on board or on chip size, so that the rest of the components, which are like power amplifier, linear amplifier, these converters up and down, these things I will be able to accommodate not one, but multiple, but not only multiple, but they work on different, let us say, frequencies, operating at a different standards by the baseband is not a big problem, because the integration on the VLSI is much faster. So I can parallelly implement many interfaces together. You will actually see, I take one case study, so I think you'll be able to see. So this is again something which I don't think I need to kind of say much to many of you. You are faculty, so you actually know. But many times when I do on the back end, whether in an ADC or other processing, when I want to do, I have to absolutely take care of the accuracy of the signal and also precision of the signal. Accuracy, of course, tell you that, for example, if I were to kind of point here, now these 4 points that I acquired, they're very accurate because they all come very close to my actual, let us say, the reference value, right? So this is very accurate. Unfortunately, it's not so good in precision because these different measurements are spread over different places. That way, this is very nice because this is all very precise. All my data acquisition points are very close by. Unfortunately, they're all quite far away from the reference value, so they are actually low accurate. If I want to put it in a slightly graphical form, if I were to measure a value which is actually given by the reference value here, and if I have high precision and high accuracy, I expect all the measurements to fall on here, and all the measurements sitting right on the delta function, and there is no deviation. But of course, as we said here, there will be accuracies defined as let us say the difference between the actual calculated or the reference value and what I actually obtain. But at the same time, the obtained value also doesn't follow a simple delta function, but there is a kind of a spread. Obviously, I would like to have the spread. Sometimes these are called, Gaussian distribution or Bell distribution. If the precision is very nice, then I get a very narrow distribution. The precision is bad, then I get a wider distribution. So that is how we define accuracy and precision. So the hallmarks for many of the strategic applications, radar, space, and even science instrumentation, etc., this is very important that both precision and accuracy are kind of maintained well. Because if you don't acquire the data properly, no matter how well you kind of massage the data and do some software refining of it, you can never really get the signal that is lost. So it is very important when you build the backend systems, especially using electronics, you need to always keep in mind, in order to get a good resolution, you should get both accuracy. You should keep your eyes both on the accuracy and precision of these numbers, of the acquired data. Okay, so of course, let us formally define what microelectronics is. Of course, it's how you kind of study and manufacture very, very small electronic components, okay, or circuits sometimes, which are all obviously made from semiconductor materials, silicon, germanium, gallium arsenide, whatever. And sometimes many of the components, like today you talk about resistors, capacitors, etc., right? I mean, they're so-called passive components, discrete components. But you know that I can also build let us say, a resistor inside as a kind of as a track inside the integrated circuits and so on. So not only that, unlike on a circuit board or a macroelectronics where I take wires to connect point A to point B, hereby we use what you call the wiring, the wiring technique, which is so-called wire bonding. Very, very tiny wires bond between the cells of an integrated circuit into let us say the connecting pins and so on and so forth. Now, as these technologies have improved, as I already said, the scale of the microelectronic components come down. As at smaller scales, it becomes extremely important, the intrinsic circuit components. Okay, because for example, if I have a big circuit, whether I connect to long wire, short wire, etc., doesn't matter. But if I shrunk the whole thing, even the interconnecting wiring becomes very, very significant. So I should also reduce the interconnections between components, right? Now, the goal of the microelectronics design engineer, of course, is to find these. When I shrink the size of the components, and when I increase the operating frequencies, the effects that are going to, the fringe effects that are going to happen, the frequency effects on components, the parasitic effects that are going to drive on, it is very, very important to compensate, because the circuits then simply do not work. And if I now, on top of that, if I say, oh, you make small devices, faster devices, low power devices, cheaper devices, no, I mean, I can always say, right? So then it becomes much, much harder for VLSI design engineer to take care of. While at high frequencies, I have to take care of all significant effects that the frequency is going to play, which I don't have to care at lower frequencies. But at the same time, maintaining all these metrics also becomes a big deal. Okay, so of course, there are nowadays excellent tools that are getting available more and more. What you call all put together is something called EDA tools. EDA stands for Electronic Design and Automation. Right? Okay, so how do you kind of go down and kind of start building let us say, electronics by yourself. So I'm not talking about going to market and buying certain amplifiers or op amps or whatever. But if I were to design my own chip, you can even call that as application-specific integrated ICs, integrated circuits, which are called ASICs, right? So how do I go about designing one for my application, my RF application? How do I do it? Because it's not that I'm just doing it for fun, because for my frequency application, for my level of integration, it is quite possible that I don't have a chip in the market which I can bring it like a op amp or whatever, and then put it in my circuit and work. So therefore, you need to kind of design them. Now, if I'm designing a low noise, let us say an amplifier that is sitting at the front end of receiving circuit, okay, I had to sit down and say, what are all I'm looking for? I'm looking for, let us say, the so-called impedance amplifier. This is the best in terms of low noise, and I also want to something which I can match with the front end. And then I also would like to have as much gain as possible. At the same time, I want to minimize the noise that is transmitted. So therefore, I would like to have the entire structure as a differential structure rather than the single-ended structure, so that I can cancel out the common mode between them, right? Okay, so that means I'm now thinking about having a transimpedance amplified stage followed by a high gain. I can have many stages. Differential amplifier need not be one stage. I can have many stages, and then this is where I have, let us say, my amplifier output. Okay, and I can have number of channels in one chip. You remember I said that nowadays people don't talk about just having one receiver on one chip. So I will have multiples of them. So I would like to have them addressed by many channels. Okay. Now, of course, many times you want to process as data. I would like to convert that analog signal into maybe sometimes logical signal. I use what is called comparator. I understand that you have a detailed session on comparators, high-speed comparators. So I'll not spend much time, but except to say that even if I want to transmit that data, digitized data very fast, then it becomes very important that I should be able to have not a single-ended output, but so-called low-voltage differential system. So I transmit the data on two wires, once again, because I want to maximize signal to noise. If there is a electromagnetic pickup, I ensure that my signal doesn't get attenuate or get noisy. And sometimes you also want to build some other electronic components like multiplexers and so on and so forth. But what I'm actually trying to show here is when you want to design your own chip, the blocks that you need to think about, various blocks that you require for your application or functionality, is something which you need to think about. And when you think about that, it's not just a block, but then when you sit down, then you have to really look at what are my pulse input signal characteristics. What is the gain that I expect? What is the signal to noise I expect? What is the power budget that I have? And so on and so forth, right? This becomes very important. Now, of course, as I said, the EDA tools are going to help you in the basic design, in simulation, in performance simulations and so on. So that is something which you get very good confidence by saying that, I have designed a chip which I think has passed certain simulations. So I have more confidence that when I get this chip made in a foundry, it's going to serve my purpose. Okay. So similar, something like that, when you take design and send out to a foundry, let us say you get the chips done. So these are your ASIC chips that you got made. Of course, you will go ahead and then make a circuit board just like you make for any other applications, buying that. And what is actually important in this, if you look at very, very quickly speaking, as I said, you have to decide, since you're going to get this fabricated by a foundry outside somewhere, that foundry runs in what is called a process. Process tells you what kind of silicon process that is in operation at that particular time. For example, 350 nanometer CMOS. You remember we talked about CMOS. You then say, what is my input signal dynamic range? What I expect this signal to go into? Then, what is the gain I'm expecting? What is my frequency response? And and so on and so forth. And, I want to obviously package it in very small space. And most importantly, I don't want to consume a lot of power and this and that. So all these specs and internal circuit becomes a major thing that you need to do. ASICs, of course, is a time consuming. It's not that you can just design just like that, send it, and they send you back the chip in the first lot, it will work. Many times you require iterations, maybe 2 or 3 iterations before you come back with the final thing. So I can tell you from my own personal experience, starting, I didn't even start here. I started even much more discrete circuits, but this is, you can say, something in between. And sometimes people also say what is called modular instrumentation. So some company makes circuits for you. You just buy those modules, put it into your crate and use it. Of course, this is easiest, but it is expensive. Other possibility is that you start making so-called discrete. But as you can see, they consume more power and they also take more space and you can't integrate them well. So we started with what is called hybrid microcircuits. So it is like a small capsule. If you open the top lid, there inside, there are circuits which are very similar to this, except that you use very tiny components. And then when you kind of, when you pack it, it looks like a packed integrated circuit to you, but you can even open the pack and see that is nothing but the same discrete things here. Okay, much better compared to this, because this is only about an inch by maybe about ½ inch, but it consumes a lot of power. Then we designed really the mixed signal, like what I showed you before, the preamplifier comparator ASICs, that what we need as per the design, and they were made by a foundry in the European countries. And similarly, we also, of course, developed quite routinely not only the mixed signal ASICs, but also purely digital signal, where we also measured some timing between the oscillating frequencies, for example. Okay, so these are generations of signal processing electronics. Obviously, you can't run on this kind of circuits or this kind of circuits. Forget about 300 gigahertz and all that. You can't even run 1 gigahertz kind of signals here. But here, yes, you can run, I won't say still RF frequencies, but something like, less than about 10 or maybe 6 or 7 gigahertz signals, you can process them. We'll see that very soon. So when you talk about, processing, as I said, this is the front end, of course, but then the very next question that comes to the main component that comes to is about how I can kind of convert the data coming from what I had before into digital. So again, this I will not spend much time here, because this is again a very basic method of analog to digital conversion. In a way, this architecture is an improvised architecture, which is a very classical architecture, where instead of doing the so-called successive kind of approximation method, where you build your signal here and give a reference here, and then take the data out, and then use a DAC to produce this reference, again change it, and it's like 1 bit at a time. You keep flipping from the most significant bit to the least significant bit, but 1 bit at a time. So that's why it's called successive approximation method, right? But here, what you actually do is a more kind of a useful for a low frequency, relatively low frequency signals, but very, very, very good linearity and accuracy. Remember, I was talking to you, precision and accuracy are big things. If you really want, people generally use the sigma delta, where when I give this input signal, okay, depending on the output, I'm going to kind of have an integrator charging this, and the comparator is, remember here, comparator is nothing but 1 bit ADC. That's going to give me either an yes or no. Based on that, I'm actually going to check for 1 bit at a time. So which means if I give no input at all, let us say Vn is 0, no matter what V reference I join, the output will always remain 0, 0, 0, 0, because compared to any Vref, I always get 0. But let us say I give Vin as the maximum dynamic voltage, right? Okay, so then I'll get, obviously, no matter what my Vref is, always I get an output as 1. So this is 0 and this is 1. And now if I give obviously exactly like half of the dynamic range, so one side I get 1, then I feed back and I get second time I get 0. then I 1 and 0 and so on and so forth. So it will kind of keep oscillating. So what it means is it's like a code where you have basically the more the number of ones, that means the data is kind of more higher the input voltage. Why this I'm taking time to explain, because it might look very classical architecture which is actually there in textbooks, right? But the important factor is if your main focus is very high accuracy. Okay, later on we'll see many architectures which are extremely good, very fast, but you have to make a compromise about the accuracy of the input system. So the classical systems are very good for high accuracy and linearity, but when you want to do faster, then you might have to make some compromise. You remember in that circle we talked about the linearity, low noise, and so on and so forth. So this is one end of that. Okay, now when you talk about very fast acquisition, you can't do this. Just now we realized that this is like a sequential circuit. So I compare, I integrate, then I kind of, generate a 1-bit ADC, then I kind of, this is a flip-flop, then I come back, then once again, I flip between 0 and 1 and so on. So this is a highly sequential circuit. But if you are not in favor of that because you need high speed, then what I do is I don't do one step at a time, but that input, whatever I given, I'll give in parallel to so many comparators at a time. Okay, but I ensure that the comparators thresholds are binary coded. What do you mean by that? If I have a R here, then I say this is R power 0, R power 1, R power 2, R power 3, 4, 5, 6, etc. They're binary coded. Now, when I give my input the way I gave here, you can expect that only those ADC comparators whose threshold is above the signal is above certain thresholds of some comparators, the output will be 1. Those others will be 0. So I'll actually instantly produce the outputs that are there as the outputs of this comparator. All that I need to do is take this data into, let us say, an encoder, right, and produce this data. But everything is instant or flash or parallel, right? That's why it is called a parallel ADC or a flash ADC. Of course, the only problem obviously with this is here you have just one comparator, but here you will have, let us say, 2 power n minus 1 comparators where my number of bits of the ADC is n. So if I say 8 bits ADCs, then I should have 7 comparators and so on and so forth. But then the question now we should ask is, since the cost of electronics, cost of integration is kind of coming down, you don't mind having parallel ADC, flash ADCs, which was not true earlier, right? Now, just now I said that this kind of architectures are very classical and you may or may not like this. So I want to use, by the way, sometimes I take some examples of some actual chips or circuits from some manufacturers. It is only for kind of teaching you some concepts. I'm not at all obviously endorsing using some brand or the other. Okay, please don't misunderstand on that part. You will have equally good ADCs in the other companies as well. Okay, so you don't have to take that company logo as seriously. Now, if you look at this, now I'm talking about one ADC for especially suitable for RF applications these days. You remember we talked about supply voltages should be very low in that circle. Obviously, we would like to have a better precision with kind of 12-bit, 14-bit, 16-bit. Obviously, we also want to operate them at very high frequencies. I don't still consider these to be extremely high frequencies. We are only talking about 2 or 3 gigasamples per second, right? And if you then, of course, follow a Nyquist criteria, you're actually only talking about 1 or 2 gigahertz signals you're processing. But what I want to kind of demonstrate here is that the architecture, if you really look at, if I have the data in, that is a differential architecture that has gone in Vin plus, Vn minus, the proper ADC core here is very small one. You can really see, okay? Rest of all that is a Farron failure in terms of controlling the chip, the controlling the output, controlling the converters, controlling the configuration, and so on. what is this architecture that we are talking about? We are now achieving this higher and higher speeds by what you call pipeline. Pipeline architectures are very popular these days, right? What are these? What do you mean by that? Olden days, if you remember, if I'm acquiring data using an ADC, I take a signal and I take my own sweet time to digitize that data, send the data on my backend or processor or whatever, then take the next sample. Until I do that, the entire time that the ADC takes is sometimes what we call dead time, for example. Olden days, I used to work with ADCs which are like 8 microseconds and so on. Of course, 8 microseconds in 1980, you may say, I mean, they were extremely fast those days. Now, if I say I'm using an ADC which is 8 microseconds, people laugh at, right? Because 8 microseconds, lots of things happen in a big system these days. Okay, now how do you improve this? Of course, you increase the clock frequency, but there is certain limit. So what you do is you do this pipelining. Pipelining means while I'm acquiring data, in the front end is acquiring some data, the other stages, the remaining stages, whatever are there, many stages are there, then you start operating with those previous samples. It is like, let us say 8 people standing in one behind the other. Somebody is doing something while somebody is doing the behind person is also doing based on the previous data. The behind person is doing based on the previous one, and so on and so forth. So it's a concurrent processing. So therefore, in a way, like if I have eight cells, I'm actually increasing in some way, not exactly 8 times, but little less than 8 times the speed. So these architectures have become very popular these days. It's called pipeline stage, except the last one where after I finish that, I should be able to kind of immediately send the data out, right? So what I kind of do every time is that every stage, every flash resolution flash ADC, which is connected to the it's a kind of a switch of capacitors basically. Okay, so I will have the ADC data which is coming at any stage is compared with a switched capacitor array of a DAC that between each of the stage, and that data which is difference between what you saw this, right? You saw here. Okay, so you kind of compare between the data of that stage and the DAC output. Similarly, also I do that difference between that stage output and the DAC output, and that residue, whatever is there, you amplify that residue and then bring that data front to the flash input. So that is how it goes to the next stage and so on and so forth, right? So this is how these so-called pipeline devices are able to kind of work very well. Obviously, the proper synchronization between each of these stages, it becomes very important. And of course, you also have to take care of, let us say, all the error correction, encoding, everything to be taken care from one block to the another block. And of course, they also have to be, for example, the output stages have to be powered separately so that depending on where I want to drive this signal, ADC output you want to drive to some other circuitry. So I should be able to kind of buffer the output. Now, I said briefly that the pipeline architecture is the key for high-speed devices, but one very nice architecture which is called so-called fast detect is actually the key block of the modern ADCs. For example, if I have a signal which is actually like this, okay, I have a little peak here, I have another signal here, and I have another signal. This is what my ADC is seeing. Okay, now in this kind of ADC that I kind of shown just now, okay, when I kind of use with an amplifier whose gain I can kind of vary. Remember, I said before the difference between the ADC output and the DAC, the residue is what is amplified and put back, and the variable gain, the gain keep changing based on that. Okay. So in this case, it actually shows how rapidly, okay, by which the detection bit is kind of programmable. Okay, now let us say I program the one bit, just like a comparator. I say this is my upper threshold. Okay, this is my upper threshold. Okay, and then what the bit, the so-called fast detect, very fast detect will be set at this point of time when the absolute value of the input signal exceeding. Because now you can see it is exceeding the the upper limit, right? Now, but at the same time, the same bit actually gets cleared only when the absolute value of the input goes below the lower threshold. I have lower threshold here, I have upper threshold here. Upper threshold is set here, lower threshold is set here because this signal has gone below. It doesn't go here because even though compared to this signal is much smaller, but okay, you can, by the way, the inside which is you have a carrier frequency. That is because your threshold is actually set here. But you might argue that, okay, once a peak is done, there is a big difference between the peak here and the next one. Okay, so this is what is sometimes called dwell time. So I actually set saying that, look, I mean, even if the time is more than this, don't reset it. So it will actually keep holding until it receives this. And of course, I can change the dwell time the way I want. What I'm doing here, I'm actually doing to speed up the pipeline ADC. I'm able to get the peak position very quickly, detect fast, and then also detect the lower threshold. And the difference between them gives me immediately what is my dynamic range. Then I adjust the gain to suit such that I get the best gain for each of my circuit. Next time it might happen that I get a very small pulse and I may get a different gain there. So I keep kind of changing the fast detect signal up and down and apply that to my rest of the processing. So modern days, the ADCs architectures have become extremely popular and extremely fast because one is the pipeline architectures. The other thing is using this kind of architectures where you kind of fast forward the kind of circuitry acquisition. Okay. There is another very nice method which I just now mentioned called switched capacitor array, but I didn't define or told you what it is. See, if you can see on the screen, there are bank of capacitors here, and this is going to be my signal at the input. Okay, and the way I'm going to do it is I'm going to run an animation. Okay, my signal is somewhere given here. Okay, so what it is doing is you can see that each capacitor is actually switched at every 200 picoseconds. Okay, so that means I'll run it again. So you can see I have given a continuous signal here, but an instantaneous value of that signal is held across this capacitor at every 200 picoseconds, for example. Now it says the waveform is stored because whatever input waveform I have given like this, you can see those dots are telling you, those dots are the points at which the voltage is actually held across the capacitors. Okay, everything is frozen. After that, I'll say, now you go ahead and then take the voltage across each of these capacitors and digitize it slowly. I don't have to do it very fast. And if I can reconstruct this pulse, you can see this is my actual input pulse, and I was able to kind of reconstruct pretty well. Now, because there is a bank of capacitors and array of capacitors, and they are being switched at whatever frequency I want. The frequency is only decided by these small gates. You can see the gate delay from input to output is what is actually giving me that delay. So these are very nice because you can make extremely high speed digitizers, okay, which are somewhat different to different technology, if I can say, compared to, let us say, parallel ADC, flash ADCs, and the ADCs that I talked about. The ADC, pipeline ADCs are also a good construction because you can do things in parallel, okay. But what is important here is that you can actually sample them at very high frequency. Okay, so this is called SCA or switched capacitor array, right? So one could actually build, what we did was we built an ASIC using such kind of an architecture. You can actually, a very small chip, about 5 millimeter by 5 millimeter. It can take 9 channels, so 9 transmitters, 9 receivers, differential inputs. It can actually sample the data at about 6 gigasamples per second. Okay, what is even more important is that if you build such an ASIC chip, which is actually shown here, then I can, of course, there is an ADC here as I showed you, and I can also attach an FPGA, which I did not describe to you. I'm going to describe very soon. Then I can putting a DRS, the digitizer attached to an FPGA, which is an VLSI device. I can make a very, very compact system, and I can store the data locally. So I can build extremely fast digitizers, at least to a level of about 5 or 6 gigahertz samples. Okay, so this is very nice architecture, because the size of this board will be hardly about 1 inch by 1 inch. Okay, I can actually make very, very highly integrated thing. Yeah, just now I talked to you about using field programmable gate arrays, which are not like ASICs where you design the chip yourself, but field programmable gate arrays, as many of you know, is a chip that can be programmed in the field, and it is nothing but a kind of array of thousands and millions of gates. Okay, so what is the architecture? The architecture is, I have many logic blocks. A logic block is nothing but like a logic that you can implement, like a combinatorial logic, whatever you like, the gates and so on and so forth. But this is like a block that exists for you, which you can program the way you like. You can load any truth table inside the block, and it will work like that circuit. Okay, if you don't like that logic block today, you can take it out and you can put a new logic block in that. Unlike the gates which you buy from a market, if I buy an AND gate, obviously it will remain as an AND gate forever, right? I can't change it to, let us say, OR gate. But here, when whatever logic that I'm going to fuse inside these logic blocks, instantly decide how the circuit is going to work. Now, you might say that output of each of the logic blocks can also be routed to the inputs of other logic blocks by using the routing matrix. Ultimately, as an integrated circuit, you want to bring the outputs to pins. Any IC has to have pins. So these are the pins. Okay. So how does it work? It works by programming the logic here, by programming the connections, the routing you call, right? And then bringing ultimately the outputs onto the pins, so that when I solder this, when I mount this FPGA on my circuit board, I'll be able to kind of get the final outputs. Okay. So this is what I was saying, that all these logic blocks are like something like lookup table. What do you mean by that? If you see bottom here, I'm actually talking about simple gates here. There's an AND gate, there's an OR gate, and I'm saying I give ABC inputs, and then I want truth table y equal to A and B into C, for example. Then I generate the truth table. This truth table, I can put it in my logic lookup table here. And if I give my inputs here, the output will be exactly what I expect. But suppose I don't like this. I want to change quickly. I want to make this OR gate. I want to make this AND gate. No problem. You just generate the truth table, push this one into the lookup table. I get the new functionality. So what is the key of this? The key of this elements is programmability. But programmability where? Not in the industry, but in my house, in my lab, in my school, college, or my industry. What is more, I can even make a product out of this, obviously, and I can even program it remotely, which means sitting here in my office. If I have a device in your office, I'll be able to kind of change the programming and the functionality and so on and so forth. Okay, so that is how the advantage of FPGAs, field programmable gate arrays. Okay, what is even good about this is, now if I have an FPGA, for example, let us say produced by some company, Altera, let us say, okay, inside that FPGA, apart from the logic that I mentioned to you, there are also, let us say, soft core. Soft core means what? It's like your microcontrollers or microprocessors. I can program it just like that. I program a microcontroller. If I go to a market and buy a microcontroller, how I write a C code and cross assemble and then run a code, similar one you can also run inside the FPGA. It works exactly the same as what you run outside, except that you can run maybe tens of times or 100 times faster than what you can run outside. And so which means FPGA is not only just fusing the combinatorial hardware, but also I can also run processors inside. Okay, so this is what is shown here. You can see, for example, here I'm talking about many logic blocks here, which I showed you in the earlier one. I can program all that. You remember this entire black square is an FPGA, right? Okay, so I can program all this, whatever I like, whatever processing whether it is RF, whether it is microwave, well, something else, it doesn't matter. Whatever processing I want to do, extracting the data output from my receiver, I can do all that steps here, and I can change them at will. And I can also have inside that microcontroller units where I can run programs just like I run on a outside thing. So what we normally do is when we have such kind of chips, we actually mount on. You can see this is a very tiny compared to a pencil here. It's very small board, but you can believe that I can handle through such kind of boards about 128 signals from the field. So simultaneously, I can run 128 such signals coming into, process all that data and digitize that data and then send out on, let us say, in this case, Ethernet. Of course, this is a copper Ethernet, but I also have a version which is, let us say, the fiber. Okay, so this kind of processing is possible because of the superior power of FPGAs. Now, I think I have only. I'm sorry. Can I ask how much time do I have? Professor Yesudas, can you tell me how much time?
Yes, sir. So you can continue. No harm in that.
Okay.
Okay. So one of the when I talk about integrated circuit technologies, particularly for the FPGAs that I've shown here, and I also mentioned to you about the process size, right? In some sense, to say what is the smallest size I can actually build a transistor on. You know, I was showing you 300 nanometers, 500 nanometers, and so on. One technology that has revolutionized all the VLSI circuitry is what is called fin-field effect transistor technology, or FinFET technology. If you remember, the way we build a FET device, you have a source, drain, and you have a basically a gate there, right? But this structure, if you look at, the gate is actually not one surface, but it is either one or two or maybe three or maybe four, because it can. So you actually bring the gate kind of four side of the channel, wrapping around the channel between the source and the drain. What do you get by this? Okay, you get, because significantly faster switching, it happens because there is a larger current density. I'm increasing because I'm increasing the silicon surface more compared to having a single kind of a channel between. Okay, so if I can do this, then the switchings I will be able to kind of increase tremendously by this. By the way, why it is called fin? Because this particular structure looks like fins of a fish, right? Just center around. Now, so using this, you can see the transistors. We are now talking about a gate thickness of only 5 nanometers, and then the width will be about 50 nanometers. Supposed to find applications which is much better than 30-40 nanometers technology. One of the best FinFET chip that came about even in 2002 by TSMC, called Omega FinFET, because again it's like a omega shape, right? If you look at the gate, it is like a Greek letter omega. One is talking about devices which can switch at 0.4 picoseconds and 20 nanometer transistors. Okay, 0.4. Okay, or if it is p-type, then it is 0.8, less than 1 picosecond switching. So that is exactly how today you talk about very high speed, but at the same time very tiny circuits. Intel, of course, in 2011 again came up with this 22 nanometer node with about 8 nanometer wide fins. Now, so the FinFET technology brought together two things simultaneously, which we said it is very difficult to kind of get into a kind of a bargaining issue. One is it shrunk the sizes to about 20-30 nanometers. And secondly, more importantly, it kind of increased the speeds like never before, talking about the gate delays to the level of 1 picosecond. Okay, so this is extremely a big, you can say, a landslide kind of a technology change that kind of happened sometime back. All this happened at University of California, Berkeley, about 20 years ago. And all these guys, by the way, They are all top bosses in Intel and those kind of companies these days, and they of course run their own companies. Okay, so this is the huge difference. Now, using that same FinFET technology, now talking about 16 nanometers technology, Xilinx come about with huge number of what you call ultra scale FPGA devices. I already introduced to you what FPGA is about. Okay, it has so many flip-flops, it has so many lookup tables, it has so many blocks and so on. And look at now what we are talking about starting in 1980s, where we had one FPGA had only about 64 flip-flops, some lookup tables about 128. It ran only with about 18 megahertz clock speed and the so-called 2 micrometer node. Today, we are actually talking about devices which can have 2 mega, because this is kilo and this is again 2000, right? So 2 or 3 mega system logic cells compared to here. Okay, and you can see there, just give me a second. And you can also see that apart from, I mean, I don't want to go through each one of them, but there are, the RAM sizes, there are all other, the interfaces that you can talk about. You can talk about PCI, you can talk about how many DSP slides you have, what is the kind of, RAM blocks that you have. And what is also important is gigascale transceivers that if you see, I'm actually talking about 32 to 33 gigabytes per second. And I'm telling you that this chip comes with 128 transceivers, which each one can pump data at about 33 gigabits per second. So you can really see now, just with FinFET technology, the kind of speeds, the kind of integration, as I told you, these are the chips now available for RF applications, microwave applications, where people are actually building systems using this. So I'm going to talk about two such ultra scale devices. Actually, one I'm only talking to just show you the general architecture, but the second one is more specific to our lecture today. Okay, see the so-called ultra scale structure, which is multi-processor system on chip. As the name says, system on chip is I have all the integrated elements together on one chip, and I have multiple processors. You can really see we are talking about 64-bit ARM processor here, Neon processors here, floating point devices here, and cache memories, my memory management, and so on and so forth. I have 32-bit another device, again RISC processor, coming exactly with all those components once again, and then entire memory structure, entire system functionality. And look at this. You name any interface that you want, serial to parallel to SPI to UART to CAN to PCI, USB, you name any of them, all that is built on one chip. Okay, so this is what I was saying. What I was saying is that when you have implement, let us say, the platform based backend support for your RF application, you don't have to build for Ethernet controller, let us say Bluetooth controller or some SPI controller or some other controller. Nothing is required. You have just one chip in which all the interfaces are built in. You have hundreds of transceivers. You don't have to make one transceiver, as we said. Okay, and you have all the muscle of all the processing power and enough memory, enough cache, so that the processing is very fast. You don't have to store them in the regular conventional static RAM. So these backends have completely revolutionized your RF systems. Okay, using such kind of just one slide, using such kind of devices, which you can't see, of course, they're all below the heat sinks. So some of us, when people like me, when I work in my projects, which are actually, as I told you, I work in the field of energy physics. These are the kind of big, this is just a part of the equipment. You can see a person sitting here. Compared to that, how big this laboratory setup is. Like this, we have many more units come in, and 40 to 50 million signals coming in parallelly together. So, and very, very high speed. And using such kind of multiprocessor as system on chips, we can actually build very compact, very small board, very, very high speed processing, and that happen. Of course, we use such kind of chips, as I told you, MP SoCs for our data acquisition, signal processing. But coming to more for RF signal processing, there is a counterpart here. This is more for low, signal processing. You can say low signal, low amplitude signal processing. And here we are talking about systems where you can see there also we saw quad ARM processor, both Cortex 53 as well as 5 R5 on 64-bit and 32-bit. But you can quickly see that compared to this chip, where you didn't find so many ADCs and did you see any ADCs or DACs, etc.? You don't, because this is more for conventional digital system processing. But here you will find there are 16 channels of RF ADCs, which is each one of them is dual. There are 16 DACs. Then there are, as I told you just now, there are gigabit transceivers and all this programmable logic, everything in one, right? So here, apart from that, when you kind of talk about, so with ultra scale architectures, we are talking about the RF ADCs, DACs, and also the so-called, we'll see soon what it is, soft decision FECs. It is capable of implementing a complete software-defined radio, for example, SDRs, including taking the data directly, the RF signal, RF sampling. No other pre-processing is required. You bring the RF sampling directly here, okay, and then I'll be able to give you the entire processing of that, and then implement all the logic that you need for a software-defined radio inside this programmable logic. And these are ADCs are like 14-bit. They all can operate at about 6 gigahertz, which means absolutely good, excellent noise spectral density. And another important thing is, apart from ADCs, they also have both, obviously the ADCs and DAC units also have a down converter and up converters that you will be requiring for handling the carrier frequency and modulating it. Now, I mentioned just now, basically saying soft decision forward error correction engine, which is called FEC. These are very important for wireless applications, okay, where I need to encode, decode error signal processing. For example, many times you use this for, let us say, 5G applications, sometimes used for cable modem, sometimes backhaul applications. Why this chip has been so custom designed is because this is, as the name says, this is RF on system on chip. This is specifically meant for high-end applications of the RF signal processing. Okay, a couple of slides I want to quickly go through. Please, this slide is very dense. I don't want you to read through, but I just wanted to give a picture in that. What are the main component features of this chip? Okay, as we already said, it has direct data converter systems. It has 16 ADCs, 16 DACs of 14-bit, can operate at 6 gigahertz. It has, as I told you, for decoding, encoding of especially the data transmission, especially operating in a, suppose I have system which is operating in very unreliable, very high noisy communication systems. So error coding, encoding and decoding becomes very important. So therefore, the soft decision forward error correction circuits are built in. And this is what I was actually telling you just now, that it has lots and lots of interfaces. You can really see, again, I am not going through each one of these details. You can interface to external memories. You can interface to internal memories. You can have 4 channels of transmit and receive of transreceivers. You can have, for example, USB, both 2.0, 3.0. You can also have I2C. You can have UART. You can have CAN bus. You can also have the Ethernet Max and as well as general purpose IO, which is just sorry. Uh, Now, so therefore, what it actually brings in you is that when you want to connect up this device to any external world, you have the general purpose IO, you have all the interfaces, the industry standard interfaces. So you don't have to build or you don't have to bring on board any controller chips for that communication. That's what I told you just now. Of course, this is something which I already told you about the Ethernet and PCI interface and IO trans receivers. There are very, very high, what you call low skew, high frequency clocks which are available because obviously you are actually dealing with 6 gigahertz sampling. So you also require low skew systems, but with the lower power consumption and so on and so forth. So the clock system is very, very powerful here. You have a huge amount of logic space inside, huge amount of storage space inside for signal processing. So you want to implement any protocol of any system, you actually have enough lookup tables, flip-flops, DSP slices, multipliers, RAM memories, FIFOs, and everything is in one. The entire chip, of course, you can completely configure and keep monitoring. So I can monitor the chip integrity time to time, but I can keep on configuring the way I like using the serial buses and particularly what is called configuration security unit. So in other words, what I'm actually telling is that the microelectronics industry is now geared to building very special purpose, very special purpose. The ones that I showed you before are general purpose FPGAs, but here the system on chips are very specific purpose for RF industry, microwave industry, or any such other requirement. But they take care of all the components in one and making sure the best signal to noise, best reliability, low power, high speed systems, making it very compact systems possible. So we dealt with a little bit about the application specific integrated circuits. Later on, we talked about FPGAs. A little bit comparison, if you kind of look at FPGAs are user programmable. As I said, these are fully custom built. I can reconfigure. I cannot, it is once fixed, ASIC is fixed. I will have not so much density as I will have it in ASIC. Complexity also is much more in ASIC chip. They operate at much higher speed compared to FPGAs, and they consume more power. They also consume more area. But one good thing about FPGAs is I can buy the market one FPGA very quickly, configure it and start running. Whereas, as we mentioned, ASIC takes a lot of time, and then it becomes very tough to make it in one go. Sometimes you have to do 3 or 4 cycles. ASIC development is a very, very costly affair. So therefore, it's a lower cost development cost here, but it is a very, extremely high cost. Okay. I think in whatever time I have, I don't know. I'm assuming I have half an hour time. Organizers, please let me know if it is less than that. Do I have half an hour time or less?
Sir, in another 15 minutes maybe.
Excuse me?
Yeah, hello sir. Another 15 minutes.
How much?
Another 15 minutes, sir.
Yeah.
15 minutes. Okay, fine.
Okay.
So I'll try to little bit speed up just because here I'm talking about advances that are now happening today in the microelectronics region. We have understood what kind of architectures are available today for RF industry, RF applications. But what are the things that I had? You must have already heard about Moore's law. From 55 years ago, this gentleman actually predicted the growth of electronics that is going to go every 2 years, doubling up, for example, the density inside the chip. Luckily, even today, we are actually going in that kind of scenario. You can actually really see the number of transistors that we are producing and the cost per, let us say, transistor coming down. And this has been the case so far. And you can actually see what kind of production of VLSI chips that are happening. Will not go into detail. The principle of scaling that I've been talking earlier is a very simple thing. It is actually something connected with the way we learned what a resistance of, let us say, a conductor is, right? We say RL by A, whether it is a cylindrical or it could be a cuboidal. In case of cuboidal, I will have a length and the breadth. I will have a thickness. Now let us say this is 4 and 4 by 2. And what happens if I make the length and breadth the 4 to 2, 4 to 2, keeping the thickness same? Okay. So since the length is reduced and then the area is also reduced by the same factor, so therefore I do expect, because the resistivity is the same, so I expect the resistance not to change here. So how does that work? It works because if you look at if I look at it, here we are talking about R1, let us say certain resistance where I have rho L1 by W1 into H, and similarly another R2, let us say I change the this particular configuration. Now, of course, rho is same and H thickness is same, so I will actually get so R1 by R2, the ratio is actually proportional to the ratio of length by width, length by width. Now, if I move length and width proportionately, that means make 4 and 4 as 2 and 2, the ratio of resistance remains the same. That is the simple principle which is also used for process control of process shrinking of the semiconductor industry. So I can change the same transistor size from 4 by 4 into 2 by 2, and I can actually accommodate those many, because the resistance of that device, the characteristic of that device doesn't change. So this is a very simple concept, but that is what has been running so far when we want to reduce the size of the chip. So starting way back in 1960s at about maybe 40, 50, 80 micron size, it seems. Okay. From there, you can really see there is a standard, what is called International Technology Roadmap for semiconductor. You can really see how the size of the transistors are coming down. We are, of course, somewhere here, and hence you are talking about some 10 nanometer kind of technologies today. Okay. So now you can also see as we go along, we are actually talking about going to quantum level, maybe atomic dimensions and so on and so forth. That is why it was kind of given an extension. But, now the standard of International Technology Roadmap for Semiconductor now changed to what is called IEEE. Now again, IEEE has taken this standard also into its fold. Now it is called IEEE International Roadmap for Devices and Systems. It's called IRDS, which came about only just a couple of months back. Until now, there is to be what is called IRTS. Okay, so as I said, of course, you can keep changing reduce the size, but the main process is the way you make the chip is using so-called optical lithography. That is the one which decides what is the smallest object that I can kind of inscribe. So there are also advances in the optical lithography. So therefore, I'm able to make those smaller and smaller structure. The area, the power, and the speed characteristic of transistors with a planar structure, just one plane structure, is actually improved with the decreasing of the lateral dimensions. So as you reduce the size, obviously the power reduce, the area reduce, and the speed kind of increase. So if I say, if somebody tell you that I'm actually working on this scalable technology, it actually means the people are expecting to reduce the gate delay by about 1/3, increase the density, transistor density, double it, and also what is the energy required for every transition. Transition is low to high or high to low. I want to reduce it by almost about 75%. Okay, so these are some of the major goals when you say somebody is working on scalable technologies. So starting, as I said, the way you define this is what is the kind of gate length and what is node. You remember just now I told you about node, 30, 40, 50 nanometers, etc. This is what has been kind of going on for, which is actually now almost reaching the limits of lithography. Lithography is the technique by which you etch the semiconductor wafer, the chip onto building whatever you kind of are expecting it to build on. Okay, so until now, so there used to be two metrics which is to decide what is the integration density. That is so-called metal half pitch, and what is the other one is called a gate length. Okay, in the beginning, both used to be the same one. So the metal half pitch is half of the distance from start of one metal interconnect to the start of the next interconnect on the chip. So I have many transistors. So what is the starting of one interconnect here to the start of the next one? Okay. So whereas So that means it is nothing but if I can say that it is what is kind of gate length is also measured as space between the two transistors, source and the drain. So I have source up and drain down. What is the gap here? So in that space, obviously the gate will stick, right? So that's why it is called gate length. Gate length is what actually controls the flow of electrons from the between the source and the drain. So earlier it used to be, as I said, the source to drain gap, as well as from the beginning to the first metal length to the next length used to be the same. So therefore, when somebody used to say, like Moore's law, they used to say that if I reduce, if I make 30% of the gate width, and if I make 30% of the metal, this one on both sides, it used to be like half. Okay, because it's like a triangle. I'm reducing x and y direction by 30%, 30%. Area becomes half. Okay, so using this gate length and half pitch as the node number, so that is what was serving from 70s, 80s, etc. But now slowly people are saying that no, this will not work anymore, and we have to look for other matrices. Okay, for transistors. What is that? It is actually called so-called contacted gate pitch and metal pitch. Metal pitch is the same, the minimum distance between the two horizontal interconnect, but the contacted pitch is the minimum distance from one transistor gate to another transistor gate. Okay, now you can actually see earlier we had two matrix, now we have three matrix. One is the gate pitch, which is G, metal pitch, which is M, but we also now added what is called the TIFR. TIFR means I have one. Earlier we were always talking about a planar structure. Now I am talking about structures which can come one after the other. So the first TIFR, second TIFR, and third TIFR, and fourth. So for example, if I say G48M36T1, means T1 means number of TIFRs is 1. G means the gate pitch, which is 48 nanometers, and M means the metal pitch, which is 36 nanometers. So this is how the new system came about. Why? Because now you can really see both of those are going hand in hand. Now we will be able to go past, and even at 1 nanometers, we are supposed to reach by 2028. We'll be able to kind of reach with a so-called advanced lithography technology, which is what is called extreme ultraviolet technology. You'll be reaching 1 nanometer kind of scales by that time. Now the question comes is, what afterwards? Okay, we'll see that soon, very soon. But okay, there is also another metric which is also called LMC. LMC, instead of using that GMT, you use the density of logic, which is called DL, the density of main memory, which is called DM, and also the interconnects linking very many of them, it is called DC. So you kind of use, it's called LMC because it is again having three metrics but not GMT. This is again a new one which was only proposed a couple of months ago, but this is going to serve the so-called monolithic 3D, three-dimensional ICs. Okay, just now I mentioned to you that what happens when you kind of reach, even when I make one tire means the planar, all these interconnections between the circuits take 12 layers of things one on top of other. Okay, so one integrated circuit, but that is one tire, but 12 layers are where I'm only using them for interconnection. Now people got an idea, what happens if I can build multiple layers one after the other? But unfortunately, it's not so easy to build because the temperatures that are required for silicon processing, you'll find when I'm working on the second layer, the bottom layer might get damaged because of very high temperatures. But luckily, some of the integrated circuit manufacturers found that it can, now they will be able to build two types of transistors, one NMOS, N-type, and P-type, one on top of other. And you must have heard about these so-called carbon nanotubes or CNTs. You can also use them, not semiconductor, but you can use non-silicon technology. There also you can stack one on top of the other. And there are also other techniques people are able to use. So what is this? It is now no more integrated circuits are one tire, but they are multiple. That's why it is three-dimensional. It's not just 1 and 2 dimension, but 1, 2, and 3 dimension. So that is how you are packing more and more transistors together. When you do this, one main problem that happens is how do you interconnect them? Okay, because if I take a big interconnect between them, you are using too much of space. So, for example, this technique called tungsten via, it's like a PCB. You know, many times you want to take one signal from the bottom side of the PCB to the top side, you use what is called a via. So inside the chips also you have such kind of things. Just give me a second. I think I have to. So here you can kind of see that if you want to make, you will be making, for example, if I want to connect this layer to this layer, I will have all around what is called titanium nitride, and inside that you see these lines, they are the ones which are tungsten, and that I should be able to fill from the bottom layer to the top layer, right? Okay, so that is what now is another technology if you want to make 3D chips. But the problem with this is, I will tell you that on a one wafer, if you want to kind of connect up all those connections, it will run to about 100 kilometers of tungsten inside one wafer. So that is a huge kind of a tungsten that you need to make a contact. So people actually found what is called a selective gap fill. So here what they do is they, I don't know why I'm not able to play, just a minute. Here I'm able to fill only exactly those holes which are from the bottom of this layer to the top. So you can kind of see that I'm not filling the entire gap on the top. So therefore I'm selectively filling the gaps. So these are the kind of technology where they want to interconnect from one to another so that I'll be able to gain more integration into one. So when you go to that kind of a level, it becomes important that what kind of challenges that I face. Another challenge that comes apart from integration is low power, because I want to make these devices, when I build more and more circuitry inside, I need to dissipate low power. Now the problem is lowering power consumption is not because I can increase the battery life, but also when I decrease the low power, when I decrease the power, it also becomes reliability. I will also improve the reliability of it. So therefore, I think power consumption is a very dramatic problem in all the ICs, right? So people, of course, work on various algorithms, architecture, circuits, etc. How you can kind of bring down the lower power. Sometimes people are even saying that if I have a base and if I have an emitter, if I maintain some kind of strain between these two, the charge will zip through very fast. And even though they operate at lower voltages, normally we apply voltage in order to accelerate the charge carriers. But what people are saying is that without doing that, if I maintain a certain kind of a strain, I can allow the charges to sweep through very fast. That will make even devices look faster. So low voltage, low power, but high speed. Okay. Now, when I make such kind of a big, let us say, use big FPGA kind of circuitry, and with I need to maintain and ensure that their power thermal management in some way is very important, because many of the high-end FPGAs consume anywhere between few tens of watts. So how people do it is normally when you see an integrated IC, integrated circuit, you see there are pins on the bottom. There is a lid on the top, everything encapsulated properly, and I take those lids and solder them. Here, these very high-end, like what I showed you, RF SoCs, the lid is kind of not there. So it is called lidless packaging. So you see these bottom, these circles are the so-called ball grid array, where I kind of put it on a printed circuit board like this, you can see, and the chip is going to sit here. On the top, there is no lid there. And then I can actually make an attachment, something like this, through which I can either flow cold air or even water or any other liquid to cool down the temperatures. So and then so this is the printed circuit board. This is the FPGA device. this is the kind of coupling that I'm going to put on top of the my FPGA. And you can see these 4 nodes are there. These 4 nodes get connected to this kind of a metallic contact on the top. And besides, if you can see, is where my heat sink is there. So that means I'm able to kind of bring down the temperatures really low, and I will be able to operate the entire system in a very, very, high temperature environment by able to kind of pump up all the heat that is dissipated by this. So the modern days, again, as the high performance FPGAs and other circuitry becoming, the system on chips are becoming popular, the thermal management, especially imagine these devices which are deployed in the war fields, okay, or strategic applications or radars, which are in the open. No, the temperatures can rise to 50, 60 degrees in the ambience. And these circuits draw anywhere, as I told you, 20, 30 watts focused into that few centimeter space. So unless you pump out the heat quickly, otherwise the chip will go into thermal runaway. So people are able to kind of build such kind of very novel thermal designs to be able to operate these chips at high cost, at high speed. One last couple of slides I have. So one thing I have so far told you about the transistors or MOS devices or whatever as the basic building block of the VLSI circuits. Of course, we all have learned the so-called bipolar junction transistors. We all have learned what is called field effect transistors. What is the what is the difference between them? Okay, in the BJT, you give a base current and you see a collector current, and you say the ratio between them is the beta, the gain, current gain, and so on. So this is what is called current controlled. Okay, the input is basically current controlled current output, right? Current output here. Okay, so this is what you can call it as a trans resistor effect. The resistance from input side is what you are actually changing from, one second. From this input side, you have the current, the base current, and output side is a collector current. So I'm actually changing the resistance basically from input to output. Now I have another device which is field effect transistors. I have input side which is voltage controlled, right? Voltage controlled, the gate, if you call, but of course the output is from source to drain. So this is basically like a surface charge effect, because I am controlling the basically the gap, the gate, the gap between the source and drain, and then I apply voltage, but I get the output in the current output. In both cases, the output is current. One case the current is input, the other case the voltage is the thing. So the voltage controlled, the current controlled. This also current output, this also current. So when you say transistor, that I'm actually changing the resistance of changing resistance, so it's a transistor. But why not? We also can have like I give the current here and I get the voltage output. I don't have it here, right? This is what is called a Hall sensor, Hall effect. So this is like saying current controlled voltage or signal. We don't have any device, right? Similarly, do we have a device where I give voltage input and I get a voltage output, like a electromagnetic effect? We don't have that device. So this is voltage controlled voltage source, current controlled voltage source. We don't have these two. So just like you call transfer resistor, maybe you can call them as transfer capacitor. So you can call them, this is transistor and this is transiter. Now, recently, people have been kind of working on such structures, okay, which will draw a much, much lower current compared to the devices that we build using FETs and BJTs. So therefore, this is a new paradigm into microelectronics, which is actually going to see fantastic developments in coming years. And I'm sure which will also have an applications in all the domains, but including RF circuits. Okay, so this is my last slide. I just want to say that the microelectronics technologies are concurrently making rapid progress and increasingly finding more and more applications in the RF area. So the integrated circuitry industry as a whole has followed that steady path of constantly shrinking the devices, as I told you, and also increase the functionality. That is how we are able to kind of incorporate more and more channels of transceivers and more functionality of RF circuits. Now, I also mentioned to you, starting from micron, now we are reached few tens of nanometer technologies, packing billions of transistors in one single die, and they're all running. You saw they're all run at the gigahertz frequencies, and of course, the structural complexity also is increasing, right? So the number of transistors per chip and the clock frequencies are going to, of course, further increase in the near future as the technology scales, means become shrunk. There will be new opportunities for VLSI IC designers, and understanding all these technology changes, particularly specific applications like what we are discussing today in the case of RF, etc. That will be the main criteria for defining very, very efficient chips. I told you just now how companies now kind of design system on chips specifically for one application or the other application. So of course, there are also many difficult and exciting challenges. It is not that everything is all rosy there. If you want to continue this phenomenal growth, also go past by Moore's law, the semiconductor industry will require advances not in one front, but also, the front-end process, the lithography I talked to you. This is more of a science, a laser technology, rather than, the other areas. And very, very innovative new architectures, power. Just now I talked to you about the power and thermal management for the SoC chips. So I would say that the Indian industry and engineers can't afford to lag for a long time in this space. Okay, that is my opinion. So I just want to do a little bit of publicity. Since it is an IEEE event, I would like to publicize a little bit a conference that we are organizing, a virtual conference, of course, because of the current situation. And that is coming in December, during December 4th and 6th, 2020. Some of you might be knowing, we have been organizing this for many years. Now this is the 4th conference in the series. And these are the conference topics: Industry 4.0, blockchain, electronic surveillance. Partly today what we talked is more, we'll go in that kind of strategic electronics, and then education technology. We also have tutorials in 2 of these topics. And please visit IEEE Bombay section webpage. So please submit papers and join the conference. Both for submission of papers and registration, both the links are open now. So you can kind of join. Right? Okay. So with that, I would like to thank you all for your attention. And I also would like to thank the organizers for giving me this opportunity. Thank you very much.
Yeah, thank you, sir.
Thank you.
Thank you.
Now we'll have a quick question and answer session, sir.
Okay.
Some of our participants had posted this question, so I'll just put it across you. The first question that was posted was, what is a thumb rule for selecting gain parameter of LNA?
Gain parameter? Sorry, can you repeat?
Gain parameter of LNA.
LNA. Okay.
This
This is a good question. If you remember one case study that I was kind of showing, is the front end was more like a trans impedance amplifier, right? Okay. So it is, if you see the unit that I given is in terms of, let us say, voltage per current kind of thing. So that's why voltage by current is ohm, right? That's why trans impedance. Now, of course, I mean, people generally say that if I have an input signal and if I have a characteristics of that, and in that case, the input signal is measured in terms of charge, okay? And charge by time, of course, is your current, right? That is the signal that you would like to kind of amplify, generally amplify. But one must also remember that you also need to study the noise spectrum of my input, because if I amplify at certain frequency range, the signal I'm also going to amplify the noise presented. So I shouldn't kind of aim at all the gain that I require from the system in the first stage. Maybe I kind of build a what we actually call as preamplifiers, in which I try to give a boost of, let us say there I think you saw that some 8 millivolts per microamp or something like that. And then I shape the signal or filter the signal in such a way to shut off the frequencies very selectively, because I know where my signal is. And then I kind of build a filter to cut the noise off. And then I build a post amplifier, which is after the shaping, which will come with shaping. So there's no thumb rule to say that what is the best for low noise amplifier. But in an overall scheme of things, plus you also need to think about what is your next stage in your dynamic range of ADC, for example. Now, if obviously I need to kind of, if my dynamic range of my input signal after amplification, I want to match with the dynamic range of the ADC. So if I do very small, then I will lose on linearity and the least count. If I do too much gain, of course, it will get into saturation and I lose signal. So it's not just one parameter that decides, but you have to really look at the chain, that namely which includes input, then the pre-amplifier, post-amplifier stage, and the ADC signal. So it's the parameters have to be combined. There's nothing like kind of a thumb rule, but people usually they talk about 50 to 100 as one good number, but exact number depends on system to system.
Yeah, thank you, sir. The next question which is posted is role of passive components in RF transceiver system design.
Yeah, we did mention very early on in the talk. We did say that the kind of challenge that one had is not so much about the active components, namely, which means integrated circuits, because in the RF domain, I mean, because as you go into the higher and higher frequencies, we are trying to say that the wavelength comes in the same scale as either your electronic system or even sometimes just the components that are on the board, namely like what you're asking, for example, the passive components, resistors, inductors, maybe capacitors, right? Now, those are outside the encapsulation, outside the shield, outside whatever, right? So now it becomes very important when I take a complete simulation of my board. It's not that what happens in the baseband systems or backend systems. I have to focus more on the RF components, which includes many passive components. So therefore, needless to say that I need to, when I want to choose certain components, I have to look at not just the values or let us say the voltage that it can operate or whatever, but I also want to see the devices as an electromagnetic component. So how is it, for example, how is the skin, how is the casing, and what kind of effect it is going to have on very, very high frequency system design. Okay, so these are special passive components. Resistors are also, they come of course with a proper packaging, etc. So that on top of that, of course, at PCB level, again, people take care. Forget about passive components. I mean, even ordinary tracks that you run on the PCB, or even the core material of the printed circuit board, namely we use G10. The quality of G10, the grading of G10 for systems of different frequencies, you need to kind of see, because you want them to offer, resistance, offering, let us say, proper resistance, pure resistance at lower or DC frequencies. But obviously, when you go higher and higher frequencies, they kind of start acting as a resistor, acting as a capacitor, or an inductor, or capacitor acting as a resistor. Basically pure resistance getting into reactances. So you have to keep in mind those things when you choose values as well as the quality of passive component. Luckily, as I said just now, the integration is going in this direction where you are able to kind of encapsulate most of these components under one system on chip. So you are kind of saved by the overall integrated circuit design.
Yes, sir. The next question, which are open source CAD tools available for RF circuit design?
Okay, I don't know the entire field out there. There may be many, and I have no idea because, as I said, I don't work per se in the RF field, except on the baseband side, where particularly what I talk today is more on the microelectronics side. Our system designs are, you can say, somewhere like VHF, UHF kind of bands. So we go up to about 5 to 10 gigahertz kind of signals. But I must also tell you that our signals are more like random signals, not so much of a sinusoidal clocks. Okay. So when we use conventional classical VLSI chips, what I showed you, FPGAs and so on, and of course we also build our own application specific integrated circuits. Now coming to the CAD tools for FPGA devices, usually all the manufacturers, whether you call Altera, which is now called Intel, or Xilinx, or Microcell, whatever, each one of them, they do offer their own EDA tools. As always, it happens for the low end, they usually are available for free. But if you are an academic institution, they come very, very cheap price. But for the problem comes with ASIC tools, which are extremely expensive. Some of them can go into 1 or 2 crores based on what kind of packages that you want to have in. And you also have to tie up yourself with a foundry. You have to decide that I'm going to go with iMac, I'm going to go with IBM, I'm going to go with TCMC or whatever. You have to decide what foundry you're going to ship the design to, and then you have to get those foundry files also, which also cost money. But then you will have many tools for design, simulations, at various levels of checking. So the CAD tools, luckily all the VLSI manufacturers, they have their own tools that you can use. They all are listed what is called EDA. Now, one other great thing that happened last about 5 to 10 years, which I didn't discuss today because I didn't spend any time on the programming tools and so on. Conventionally, we all know that, Verilog and VHDL are the 2 most prominent tools. But now the so-called high-level synthesis is a concept that kind of came about by saying that you could actually build the devices. It's called Vivaldo, is one such new, you can say, language that came about, high-level language, where you write your code in a very C or C++ kind of language, and you can actually down convert them into the code that VHDL or Verilog do. So it becomes very easy now. You don't have to even learn the so-called VHDL, HDL languages, and you can actually program most of the applications, especially the coding that requires inside. You remember I talked to you about huge cells and how do you actually code them as lookup tables. That programming has become extremely simple by using the design tools called the HLS, high level synthesis tools. It's called HLS.
So the next question is, could you just brief us on design challenges of high-speed data converters for 5G analog front-end?
Well, I mean, see, if you remember, I have been kind of trying to, as much as possible, to decouple a particular frequency bands on which what kind of circuits are required and so on, because I try to kind of play mostly on the back end, not so much in the RF circuits front ends per se. Okay, because as I said, I'm not from that domain. It is possible somebody else is going to kind of cover. I do see somebody talking about matching networks. Somebody, I think there are also other circuitry that are going to be covered. But I don't really think substantially it is going to make a big difference in terms of overall picture. But yes, of course, choice of architecture, choice of circuitry, components, those things probably matter. So it doesn't matter whether it is, when I go obviously on the higher and higher side, like radar applications, for example, where I go all the way beyond S-band, etc. Yeah, those pictures are still today. There's not so much of microelectronics getting into. People are still building systems largely with conventional RF circuits. But wireless, 5G, etc. Many of these networks, people are able to kind of integrate more and more circuits on the system on chip. So I don't know much about the front end per se for a specific domain.
So the last question, if at all researchers want to work in this particular domain, which of the organizations you would recommend them so that they can approach those organizations?
Yeah, this is a good question. Once again, I'll try to limit myself to the topic that I talked about. There are large number of, firstly, a large number of government, if I can say that, government controlled institutions in India. Essentially, they are semi-strategic, semi-public kind of industries or institutions. You heard about Bharat Electronics, you heard about ECIL, you heard about in Chandigarh there is what's called I think Central Institute, Central Scientific CSIO, I think, if I remember well. Of course, you have other institutions like BRC, you have industries like the organizations like the space, DRDO. These organizations, even Aeronautical Development Authority, HAL, and some are industry type, some are research type, some are strategic type. And then you also have all the research development centers of many semiconductor manufacturing giants from abroad. They have their design centers now located in India. Means all the semiconductor manufacturing design houses, they're all been there in India right now. Okay, earlier, if you say that I want to join Xilinx, you will say you have to go to US or you have to go to some other place. Now, Xilinx, for example, has not one, many development centers in India. Similarly, Intel has. Similarly, let us say Motorola has. Similarly, Texas has. Similarly, many other these industries have their design houses here, which will be a very, very good opportunity for especially younger people to go and, of course, join. But of course, you have to also have the right skill set required for these kind of industries, number one. Just going back a step back, what I told you in the beginning about the government-based strategic institutions and industries or organizations, again, all of these have fantastic tool sets, fantastic development plans, because we need them to develop them in India. So they're very challenging and extremely, I would say, satisfying jobs one can get. But obviously, once again, one has to kind of perform also to the level that one is required. So on one hand, you have all the government-run, government-controlled institutions, industries, and research institutes. On the other hand, you also have the design centers by the IC manufacturing companies. But in between these two, I would also say there are many academic institutions. For example, all the IITs, IISc, and institute like ours, which is TIFR, and many places where there's lots of research is done. It's a little bit like a not immediate application, but there is a, if you are talking about developing certain architecture, developing lithography techniques, developing low power designs, developing high speed designs, developing new material, for example, silicon, germanium, gallium arsenide, something else. Is there, just now today also I mentioned to you, the semiconductor technology packaging becomes very tough if I want to do multi-layer 3D IC. But I said, like carbon nanotube have suddenly been found that, this is a new non-silicon material. Now, where does it come from? Because there are people who did a lot of work on carbon nanotube CNTs. Now, this has suddenly got a spin-off to do this. Similarly, if you remember well, I just mentioned that one way to increase the speeds of transitions is not only applying high potential between the gates, but also by providing certain strain. It's like a rubber band. I kind of stretch, right? And if I release, then I'm not applying anything except that I pulled the rubber band here. So people are saying that if I can maintain in this semiconductor material certain strain between, let us say, source and drain, okay, that itself will pull the electrons faster. I don't have to apply big potential. Now what do you call this? You don't call this as an industry R&D. You don't call this as a strategic companies thing. It's a basic research, but it has a far-reaching applications for the future. So please remember, I talked 3 categories. I talked about government-based strategic industries and institutions. I talked about universities and technology institutions like IISc, IITs, etc. Then I talked about design centers of, let us say, IC manufacturers. So all of these offer fantastic opportunities, but you need to equip yourself with skill set.
Yeah, thank you, sir, for the wonderful session, and it's my privilege to have this Q&A with you. Thanks a lot for this. Yeah.
Thank you very much.
To our participants, both the sessions per day are over. The next session, I mean to say the second day, tomorrow, the session is scheduled at 10:30 a.m. Please do see to it that you attend exactly on time, be sharp at time. Till then, take care, stay safe.
Thank you. Good night.